Hello, everybody. Today's teaching assistant is Skinkerton. He is a blue-tongued skink. Say hello to skinks, everybody. Okay. Okay, today we're going to cover regression analyses. So what regressions do is they just take correlations a step further. With regressions, the independent variables can be either categorical or continuous, and they're called predictors in these cases because they allow us to make predictions about people on a specific outcome variable, which is what we use to say dependent variable when it comes to regressions. If your dependent variable is continuous, then you'll use what's known as a multiple linear regression. If it's dichotomous, you'll use logistic regression. There's also more complicated types of regressions, but they're beyond the scope of this class. The null hypothesis for a regression is that the predictor will have no effect on the outcome versus the alternate hypothesis that a predictor will have an effect on the outcome. So the way it takes a correlation a step further is that it can handle multiple predictors at a time versus a correlation, which is bivariate, right? It's only two variables at a time. And the way it does this is by creating what's known as a regression equation. So the standard regression equation, the simplest one, is right here. So you might remember this from high school, right? Y is equal to A plus BX. So this is literally the equation for a simple slope. In this case, it is representing students' GPA versus their stress level. So what the regression equation allows us to do is it allows us to predict a student's score on one variable when we know their score on a different variable. So if we know the student's stress level with this regression equation, we're able to predict using a regression model what their likely GPA is going to be. Now, of course, we're not going to be exact. As you can see, our actual data points are not exactly on the line, but they're close to it. So this is a model that works for the majority of the sample, but not perfectly for every single participant. So our estimates for the students closer to the line are going to be more accurate than our estimates for the students who are much further from the line. And the most important thing that a regression equation can do is it can tell us how much change in one variable is accounted for by change in the other variable. There are several different ways of wording this. You can call it a multiple linear regression, ordinary least squares regression, etc. The important thing is just to remember that your outcome variable is always going to be continuous and that your predictors can be any level of measurement. Each predictor is going to have a regression coefficient represented by the letter B. That represents its relationship to the outcome variable. And you saw that within the regression equation, right? It's A plus B times X, where X is that predictor. As a result, each regression coefficient is also going to have its own significance value to determine if the relationship is statistically significant or not. When we have more than one predictor, though, we need to do what's known as standardization. You might remember this from a few lectures ago, but basically we need to turn these regression coefficient into a standardized regression coefficient, otherwise known as beta, standardized beta. So this is now a unitless measure of the impact of each predictor on the outcome, and this way we can compare between predictors, which is more important or less important to create change in that outcome variable. There are a couple assumptions that have to be met in order for us to actually use a multiple linear regression. The first one is that we have to avoid multicollinearity, and that means we have to avoid overlap between predictors. We can test this by checking the correlation between predictors. Because some of our predictors could explain the same variation in the outcome variable, we don't want to include any that have a correlation stronger than 0.75. In that case, we want to just pick the most relevant one and leave out the others. An example would be looking at GPA and examining the predictors of number of siblings and household income. So part of that variation is going to be explained by number of siblings, part of it's going to be explained by household income, and that shared variance right there between number of siblings and household income is what's going to be our multicollinearity, and we want to make sure that that's going to be less than 0.75. Otherwise, two variables are just explaining the exact same variance in students' GPA. So another assumption that we want to make sure we meet is homoscedasticity. So that means that, as I showed you with that regression equation, how the dots were equally dispersed on either side of the line, we want to see that happening. That's called homoscedasticity. If it's not happening, if they're clustered on one end of the line as opposed to across our chart, we have what's known as heteroscedasticity. And what that does is it makes our regression coefficients less accurate. All right. Oh, and here we have a third potential variable that I forgot about, home overcrowding, which is overlapped quite significantly with household income. So in a situation like this, you would exclude the home overcrowding variable or the household income variable and not have. So the way that we build regression models, there's a few options. So option one would be just to stick in all the relevant predictors at once and see what's significant and what's not. We tend to do this when we're looking at exploratory research questions where we just don't know enough about what's happening. Option two would be to put in some of the variables that you want to control for first, and then put in the variables of interest. This is known as the hierarchical method. So we want to control usually for things that we can't change, like number of siblings, before we start controlling for the things that we could change, like stress in school and the impact on GPA. Option three is to let SPSS do the work for us, and there's two ways that they do that. So either we stick in all the possible variables and let SPSS kick out the least useful ones one by one, otherwise known as the backward stepwise method, or SPSS puts in the most relevant ones first, followed by the less relevant ones until there's no more relevant predictors, and that's the forward stepwise method. These two options, so options 3 and 4, result in what's known as a parsimonious model. So only the significant predictors are included with no irrelevant predictors, and that's what we want to aim for ideally. Let's look at an example using our data. So suppose we wanted to know which sociodemographic variables predict students' GPA. We'll use the predictors of age, sex, and number of siblings, and our outcome is going to be GPA. When we run this through SPSS, we get this table here. The first table just tells us how we input our information, but the second table is the important one, this model summary. So this is the table that tells us our effect size. If we look at this here, adjusted R-square, this is very similar to the R-square we learned about last week, the coefficient of determination. in that it does the same thing. So what this is telling us, even though it's calculated in a different way from the coefficient of determination, it still means the same thing. It's the percentage of variability in our outcome variable that's explained by our predictors. In this case, 0.034, if we turn it into a percentage, 3.4% of the variation in GPA can be explained by the student's age, sex, and number of siblings. If we were to look at our effect sizes slide, we would recognize that that is not a very good model, since it explains so little of the variation. Yep, and here it is. So looking at the adjusted R-square, you want to make sure you're reading the right column. It doesn't even come close to 0.1 because it's 0.03, right? So it is a very, very small effect size, negligible, we might even say. The next table that we get gives us our actual coefficients. First, you'll see within each row the different variables, and then each one first has its unstandardized coefficient, followed by the standardized regression coefficient, or beta. If we look at these standardized coefficients, we can see that the biggest impact on whether or not students are going to have a high GPA or not is actually here, the number of siblings. Because with each additional sibling, their GPA decreases by 0.11. That's what that negative means, that the GPA is decreasing. On the other hand, if we look at age, we can see from its significance value here at the end of the table that it's not statistically significant. So age does not have a relationship with GPA, and that's confirmed by the very, very small standardized coefficient. We've also got sex, which is statistically significant, and you can see that the standardized coefficient is actually slightly higher for sex than it is for number of siblings, but you have to remember that number of siblings has multiple options, whereas sex only has 2. So it can only increase GPA once. And if you remember our codes, I think it was 1 for male and 2 for female. So it's just saying that females have a slightly higher GPA than males, but number of siblings can increase, from 0 to 1 to 2 to 3. So this one, once you factor in the number of options, is actually having more of an effect on GPA. All right, so what does that look like when it's written up? Students' gender and number of siblings significantly impact their GPA, and here is the information that I used to confirm that. The model is weak, explaining 3.4% of the variation in GPA. As the number of siblings go up, GPA goes down, and here I report my standardized coefficient, the t-value that goes with it, and its significance value. And I report my other significant variable as well. And then I just briefly mentioned that there was no significant effect of age. All right, let's look now at the other type of regression that we have, and that is what's known as a logistic regression. So this is where we've got that dichotomous outcome variable. So my research question here is going to be, what factors increase students' risk of trying marijuana, with our outcome variable being trying marijuana, yes or no? The predictors I'm going to stick in are anything related to marijuana, use and demographics such as GPA, age, gender, race, number of siblings, attitudes towards marijuana, ease of getting marijuana, number of friends who smoke marijuana. And here I've put in a note just to let you know that the effect size for logistic regression is determined by the odds ratio, which within SPSS is labeled as exponent B. in addition to what we have here within our model summary, which is called Nago-Kirke R-square. So this does the same thing as the adjusted R-square. This is telling us what percentage of the variance in our outcome variable is explained by our predictors. And unlike the logistic regression we ran before, this one's great. If we transform this into a percentage, it's 56.5% of our variance that's explained by these predictors that I have selected. That is a very, very strong model. We rarely get such strong models in social work. So when I report this information, I'm going to report the significance value here from this omnibus test of coefficients. The model one is the one that you want to pick, and as you can see, SPSS gives us lots of very redundant information. And then we're going to look at which of these actual predictors is statistically significant and which isn't. So here are all our predictors, and here are the significance values within this column. And you can see that some of them are not statistically significant, like age. Age is not relevant, neither is sex, neither is race, but grade point average and average number of friends that smoke marijuana, and how often around people that smoke marijuana, all of these are statistically significant. And if you look here at the odds ratios in that last column, you can see that the most important variable for this is that attitudes towards trying marijuana. So those with the positive attitudes towards trying marijuana are 10 times more likely to try it than those who have a negative attitude towards trying marijuana, versus, say, average number of friends that smoke marijuana. The higher the number of friends that smoke marijuana you have, your risk only increases by a factor of 1.5, which is a lot smaller than the factor of 10 as for your attitudes. So what does that look like written up? Students who don't disapprove of trying marijuana are 10 times more likely to have tried pot than students who strongly disapprove. And here I provide my regression coefficient and its significance value, and the rest of my variables that were statistically significant. And then I explain which variables were not statistically significant. Then I explain the effect size. Always explain the effect size. The model is very strong, explaining more than 56.5% of the variance in whether or not a student has smoked pot, and is able to correctly identify 81.7% of students who have smoked pot. All right. So I've posted a few examples to Brightspace that you can look at for how logistic regressions and linear regressions are used in social work research. So I strongly urge you to skim through some of these articles. You don't have to know how to run a logistic regression or a linear regression for this class unless you want to challenge yourself for the final assignment.